Could sit for too long. Next transit är en bär, ett frikos horidon. Could sit for too long.
So, where are we now? We learned that they're dynamical systems, and the sets in the state space, sets of states are being permuted in time by some law that tells me, a time forward map that tells me where I end up. So that means I have a state space and I have trajectories in the state space. I start someplace at time t0. The law tells me what happens next, and finite time later I'm at another point. So that's dynamics of individual points and individual trajectories. But it'll turn out that what we really care about much more physically and geometrically, etc., are neighborhoods. So we have single X, its future. It'll turn out to be absurd to even contemplate the future of state in deterministic system, even when it's deterministic, because as we'll soon see, it's almost always not predictable for infinite time. There's only some finite time for which you can predict it. So better is to study what happens to neighborhoods. So we consider some neighborhood that includes a point X. And time till later, this neighborhood comes back stretched and deformed. And that's described by Jacobian. There's a linearized flow. Jacobian T. And the moment we have this notion of linearized flow, it seems not enough because we're interested in nonlinear problems, but it's so powerful that what we will do, trying to understand long-time dynamics, is we'll split it in little neighborhoods because we have good control over little neighborhoods. And then we will control the errors from pretending neighborhoods are linear. So pretending that Atlanta is in a flatland and not on the sphere. And that will turn out to be very powerful. So that's why we allow us a luxury of going back to a linear world, because there's some very enticing properties, of which the most important is the property that distortion to the linear level of the neighborhood is invariant. So there's a set of numbers lambda d that tells us about how neighborhoods behave. So done, I've done this, and now, what are we going to do with all this? So I have a grand plan. I first told you if I have a state space, this happens. If I have a neighborhood, this happens. And what I want to tell you is, if I divide this state space into a bunch of neighborhoods, so I make a map of entire state space, like map of Manhattan, and I give a name to every block here. And I say, as far as block is concerned, I'm allowed to pretend it's flat. I can use a flat chart to describe it. So our grand goal now is to learn, this is still all geometry, how to partition. So this is neighborhood A, this is neighborhood B, this is neighborhood C. Now, if you have a computer, you can be stupid and you can just do it, which is to say, I divide my state of space of state, define it in little cubes. Here we're in a room, I'll divide it in lots of cubes which are 1 millimeter on the side. And, each one will have some name or some coordinate or some, thing. And done. Now, that's what people do all the time. That's, for example, how we solve lots of problems having to do with traffic and flows, etc. We discretize, we put them on computer. And, you can do it, but it turns out that pretty soon you cannot do it because we're interested in serious problems and dimensionality of state space could be large. So dividing in a zillion little hypercubes is not very useful if each hypercube is, let's say, million dimensional. You just won't be able to do it. You'll be able to do it on a line, on a plane, maybe in 3 dimensions, and then you'll die. You won't be able to do it. So now, thinking is extra cost. This is apparently a Colombian proverb. I can explain this, my relative was trying to hire a maid in Buenos Aires, and, she started explaining the duties of the maid. So you have to clean, you have to do this, and then you have to prepare the lunch for the kids for the school. And the maid said, well, that's extra cost. Thinking is extra cost. So from now on, we'll actually have to do some thinking. It'll take us quite a while to learn how to partition the state space, and it's an, vast subject. We usually don't know how to do it. It has to be done on a state-by-state basis. And our strategy will be to, inquire from the system itself what it likes. Instead of just imposing some stupid hypercube on it, we'll say, how would you like to be organized, like this class? How do you want to do this? And that turns out to be beautiful and very nice, but it's not easy because it's nonlinear dynamics. Basically, the system itself, every neighborhood has its preferred directions, which we just computed as some kind of eigenvectors, eigenvalues. So they're natural coordinates when you have dynamics for the system. They're not my original coordinates. They're these ones we just computed. These eigenvectors tell me, which way to measure lengths naturally. And then dynamics tells me who is related to whom. If I'm this neighborhood, how to get to next neighborhood. And that's very powerful. That's called topological dynamics. So we'll spend quite a bit of time doing it. And I find, this can only be understood if you work through some examples. And I find that game of pinball, which regrettably you are all too young to have actually seen an actual pinball. How many people have actually played with a pinball machine? It's not so bad. I mean, the undergraduates have only seen it in the virtual reality. I actually went to a morning program on Danish television. I played pinball to explain chaos. They actually brought a real machine, and but it's all now long gone. But it was beautiful stuff. And one thing you know about pinball, you know that there is chaos because you know it's very hard to win a game which requires many steps. And we will now quantify this. And we'll use this to explain almost everything about chaos in dynamical systems.